Alright guys, so today in this video I'm going to kind of show you guys some basics with a solar design program called Aurora Solar. We're going to go over a hypothetical design on a random house in Los Angeles, California. I live in Washington State, so I'm not familiar with that location, but I decided I didn't want to pull up a house in the area that I lived because I might know the person. So I just decided, you know what, let's go to Google, let's grab a random house out of LA. I do not know these people, and let's create something and kind of go from there. So what I'm also going to do is we're going to come up with a hypothetical scenario where we've essentially got a customer out in LA. They've got a partial utility bill. We're going to input their partial utility bill information in Aurora, allow Aurora to estimate the rest of their usage for the year, and then create a design in accordance to that. So, and again, keep in mind I do not understand or know how solar works specifically in California. I don't know the solar laws in California. So you might see me do something that's not necessarily correct. There might be fire setbacks within California that are particular or specific. There's a lot of regulation when it comes to solar. So again, this is just a general design, general layout. If there's crazy fire setbacks or IFCs in LA or certain rules, I'm sorry, I don't know them. We're just pretending this is a general design. So first thing we're going to do is go off consumption, and again we're assuming that this is a customer in LA that's giving us a 6-month utility bill. So we're going to hit estimate. We're going to assume that this is the general area they live in, this is their utility rate, and that they're with Southern California Edison Co., and that they gave us a month from usage from January to June. So I'm just going to put in some random kilowatt numbers here. Again, I don't know this area, so I don't know what typical usage looks like in Los Angeles, California. Obviously we don't know how many people are in this house, if it's a big family, small family, etc., etc. So we can only assume, we're going to assume that in June, for whatever reason, they weren't at the house very much. And then, so for example, say we had this utility bill. This was the customer's kilowatt hour usages for the first 6 months. This is their utility company. This is the area they live in. Aurora then takes that information, tries to estimate the rest of the usage for the rest of the year and the rest of the months. So for July, it's estimating 1,322 kilowatt hours. For August, 1,264, so on and so forth. And then it estimates a yearly with the 6 months that you have combined with the estimation. And we're getting 13,233 kilowatt hours. It's estimating the yearly cost at about $4,453, and it shows you the monthly average. If you're creating proposals and stuff through Aurora with partial bills, it's generally pretty important to make sure the location's correct, the utility is correct, the rate is correct. If you're creating proposals throughout different software like Salesforce, or creating your invoices in different software, you don't necessarily need to worry about these for the proposal aspect, but you will want to make sure if you have a partial bill that this information is correct so Aurora can do its best to estimate the customer's usage in accordance to that area. So we've got their usage in. We see what their yearly energy is. The next step is to create a design. So I'm just going to call this test design. It's going to pull up. It's going to pin us right on the project house, and then I'm going to turn system items off. I'm going to turn off project location, which is that little indicator there. And the first thing I like to do when I get a project is I like to cycle through the images to see which one seems to be the cleanest and which ones seem to be the most up to date. I've done a lot of designing within Aurora. I've been designing within Aurora within Aurora for about 2 years, and I'm sure it varies upon location. But from what I've found on in Washington, Oregon, and various other locations within the United States, Bing and Google Imagery tend to be the most up to date, and then Google HD tends to be the least up to date. And I can give you an example of this in this particular one, because if you look at this Google HD imagery, there's a bush right here, or a big tree. And if you go to Google Imagery, it's gone. If you go to Bing Imagery, it's also gone. And you can pretty much assume that that's newer imagery. More than likely, a tree did not get planted or grow that large within that short period of time. Chances are it was removed. So I've looked through this imagery. The Google imagery is a little distorted. You can actually see the side of the house, so I don't want to roll with that. The Google HD imagery is a little distorted too. It's not terrible. And then the Bing imagery, in my opinion, is super clean. There's just a little bit of shading on this end. But since I know what this general structure looks like, I'm going to roll with that. I'm going to roll with the Bing imagery. So first thing I'm going to do is I'm going to design the main portion of the house. All right, so what we're going to do is we're going to start on this edge here. We're going to go to this edge here. You can see where it kind of connects right here. So you can see where it ends, where this part of the roof actually ends. Sorry, not connects. I'm going to go down here, finish it off, and square it off. I'm going to make sure that ridge line looks centered. It looks really centered. Delete these two sections of roof so we can see how centered that ridge line is. Now that I've got the main section of the home design, the next thing I'm going to do is turn on LiDAR, which is the laser imagery function, and do my best to match the pitch of the roof, the design, to this actual LiDAR silhouette with the pitch of the roof. So I'm going to zero out LiDAR just to make sure. Actually, that was almost perfect. So LiDAR is pretty centered. I'm going to then lower this roof face until I see the eave peek through. So there you go. You can kind of see right there where it connects. You see that? That's generally where I found the eave of the roof is, which is the bottom section of the roof. It's the roof, the lower section of the roof. I don't know the best way to describe an eave. I'm trying to think of it right now. But if you Google an eave, you'll know what an eave is. So from there, I know I have to pitch up because you can see this pitch is pretty steep. So I'm going to increase the slope until it seems to match up, and right about there is where it matches up. Now, it is a little off, and I can tell because you can see it's a little leopardy here, and then it's fully covered here. So LiDAR is a little off, but overall, you can tell the pitch is 12 by 12. If I actually move this X offset probably to like, let's see, does it have to be negative or positive? If I move this, you can see kind of how it moves around. And then if I lower this a little bit, you'll actually see it just dip right in. So it's about a 12 by 12 pitch. So we've got that main section. That's a very steep pitch, by the way. As far as I understand, you typically have to get a crane or something special to install on a roof that is that steep. I know the company that I work for tends to have to charge a little bit of extra labor and cost overall because it's just more difficult. Anyways, we've got that main section modeled in and matched to LiDAR. Then we're going to jump to this back section. Now this back section is going to be pretty interesting because I can already tell the pitch on these areas is probably going to be different than the pitch on the other sections of this roof area, but we will see as we get it designed. Again, this is kind of shaded, so I'm going to have to eyeball this area, but in general it's pretty much a square. We're going to delete this back end. Oh, and maybe well, let's see. So it's there so far, and then same concept. Now this one we're actually going to drop down to line up the eaves. Like that, and then we're going to pitch up. Maybe I was wrong. Let's see. So let's do 7 by 12. Lower that. Oh yeah. Oh well. Yeah. It looks like that's probably about what it is. So it's a 7 by 12 pitch, which is also a fairly decent pitch, but as far as I know, you don't necessarily need any extra equipment to install in a pitch like that. That's actually a 30-degree pitch, so a 30-degree pitch on the roof, 7 by 12 slope. So we've got that section modeled in and matched to LiDAR. The next thing we're going to do is model in this dormer. Now there's actually a couple ways you can do this, and there's actually a couple ways you could have done the other roof section behind, but I'll show you an example on this. So you can either trace in, well actually, you can either use this tool, do a gabled dormer, kind of line it up, move the lines accordingly, and kind of mesh it up this way and then hit convert to roof. I personally don't like to do that. I haven't found it's the most efficient or easiest way for me. What I like to do is I just like to design the roof in like usual, just like I did with the other roof faces. So I'm just going to make a square, delete these along the ridge line, and the pitch is going to be a little different on this too, probably 7/12 or 12/12. We'll see. Same concept here. We drop this down till the eave starts to match. Now this one's a little difficult. I think it's probably about right here. And then, well, actually, you can see a little bit better on this side, so this might be a better point of reference. That might be about where it connects. And then this is going to be a crazy pitch. There we go. It's about 17 by 12, maybe is what it looks like. That's kind of crazy. Might be 16 by 12. Yeah, probably about 16 by 12. So that's a pretty crazy pitch. Also probably going to require a crane. If it can even be installed on, I'm truthfully not sure in that particular case. I do the designs. I don't tend to deal with the installation. And it'll probably be the way that it is with your solar company, unless it's a very small solar company and everybody's doing everything, in which case, good luck. So we've got that dormer, and now we've just got one more dormer to do. I'm going to do it the way I like to do it, but again, you could use the dormer tool. Just going to square it off. cannot stand when they're crooked, so if this ends up looking fairly crooked, I'm probably going to modify it. This one, the pitch didn't look quite as extreme, so we'll see. Again, kind of tough, this one. Maybe this one is pretty extreme too. We'll see if that's where the eave is, because it looks like that's probably where it would be. Oh, oh. This one's a little tough, because the LiDAR is a little off, so I might have to go off the ridge lines here and how that lines up. But overall, that looks pretty close. That's a tough one. So this one could be off a little bit. Not going to necessarily be the end of the world. Could be if you're really relying on having a set amount of panels there. But generally, when you're working in solar, you use this for your initial quote. Then you have to go through and actually do some engineering drawings, some CAD drawings and stuff like that for permitting and whatnot. So not the biggest deal. It's very steep pitch, could be off a little bit. To me, it looks really close. So we're just going to roll with it. It looks pretty close in the design too. So we've got the baseline of the house designed. I automatically did this out of habit. I modeled in an obstruction, which is this chimney. I will show you guys how to do that now. So the next step would be typically modeling in obstructions. So turn on LiDAR at first. I don't really see any that are lifted up, well, except for this one. So this one's very clearly got some height to it. So we'll model it in, kind of lower it into the LiDAR silhouette. These other ones, I'm just going to flush mount because they don't have any indication in LiDAR that there's anything really sticking up. If I see a shadow or something like that, or like in this case, I'd match it to LiDAR, but since I don't, I'm not going to do that. So I'm just going to model in all these other obstructions and click this flush button to flush them out, and that flushes them against the roof instead of making them actually have like a real shading profile. It basically just blocks off that section of roof from panels rather than creating a shading. This one will have a little bit of shade casting this way. But yeah, so we're going to finish up these obstructions. I'm going to Control C, Control V this one to copy and paste it because it's about the same size. Can't really tell what they are, but we'll get them marked off. And there we go. So there we have the house. Now the next thing I'm going to do is I'm going to pretend or assume that LA has some type of fire setback code. Now what I'm going to use are 2015 IFCs. I do not know if California requires these or has these, but typically what those are going to be are 1.5 feet on the hips, 3 feet on the rakes, 3 feet on the ridges, and 1.5 feet on the valleys. We're going to turn that on, and that gives us kind of the borderline of where we can place panels on this particular house. So we cannot go into any of these setbacks. The 2015 IFCs, from my understanding, are typically for firemen. If the house is on fire and for whatever reason a fireman has to get on the roof, they need pathways or walkways that are clear of panels to walk on, and that's what these are. Whether or not it seems to make a lot of sense, I'm going to keep those comments to myself. Next step, we're going to turn on LiDAR and we're going to start modeling in shading. Trees, anything that could cause shading on the house. Typically the most excessive shading comes from the south. Just looking at this neighbor, I can see they've got a flat section of their roof that goes over a good portion of the neighbor's roof, and their house kind of peaks out, doesn't peak over, but it's over certain sections of it. So to be thorough, I'm actually going to model in part of this neighbor's house. Now, luckily, they've got a pretty simple layout of a roof. They've got a flat roof, or several flat roof sections, and then several non-flat roof sections. So I'm going to model in a flat roof, get it up to LiDAR about there. You can tell this main section is pretty flat too, or completely flat. So we're going to model in this main section as being flat as well. Same kind of thing. We're going to turn on LiDAR, lift it up. I'm just going to lift it all the way up to the top of the LiDAR silhouette to account for anything and everything. I'll do that with this one as well, just to be safe. And then this front section, you could tell it's like a pitch section of roof. It should look something like this. There you go. Same thing with everything that's got a pitch. Lower it down to the eave, then pitch up. And it's probably about a 6x12, might be a 7x12, but we'll roll with that. And I apologize, guys. My headset fell asleep because even if I'm talking in it for whatever reason, after 30 minutes of no sound, it decides to shut itself off. So we've got the house south modeled in for shading effect from that, but we also see that there's some trees in this neighborhood that we're going to want to model in just to make sure that we don't have any major excessive shading on this customer's roof. So of course I select the tree tool and I start just modeling in the trees. Now, I love what Aurora's recently done. They made this update a couple months ago. Did not used to be this way, but now when you model in a tree, you kind of go in the center and do a circle, and when you let go, it pops up towards the top of the LiDAR silhouette. So then all you have to do is lower the crown height from there. This is how I personally model in trees and how the companies that, or the company that I work for models in trees. Because it seems to be the most accurate way to model in trees. Um, so yeah, or I guess I can't even say that's the way that the company models in trees. That's the way I model in trees when I work on designs for the company that I work for. Um, I like to cover the entirety of the tree. My philosophy is trees grow and LiDAR is outdated. So if you've got trees and they're still there and LiDAR and they're a certain size in LiDAR and you make them a little bit bigger, that's going to be a lot better than not modeling them in large enough and then the customer getting something that doesn't reflect proper shading values. You want something to be appealing for a customer to buy, but you also don't want them to be pissed off when they get it and it doesn't function the way that you sold it to them or the way that you promised it would. Some of these trees are bigger than LiDAR because, like I said, trees grow. So when I run into situations like that, I just go the full span of the tree and just try my best to make it the size that I think that it would be. Got a big tree there. And this one in particular, I'm almost tempted to even model in, and I'm going to model in the house north as well. Typically, you don't have to worry about north shading so much, at least in this part of the world. But because that house is kind of towering over, I'm going to model it in as well. Just the baseline of it. Not going to get too crazy because don't need to get too crazy. So at least it's a fairly simple roof layout. We'll use a tool. You guys haven't seen this tool in the design that we just did, but this is the vertical fold tool. So when you see a roof face like this and you need it to fold in to have this section of the roof here, use the vertical fold tool and it does something like that. Just as a heads up, delete this back roof face, and then the other thing we need to do is get this matched up. So same thing, line up the eaves. That's about where they're peaking. Again, you can see right where this break happens about is where it is, and it's almost pitched exactly correct. This is either a 4.40 by 12 or a 4 by 12. I'm going to guess it's actually a 4 by 12. So we're going to roll with that and lift that up a little bit. This tree appears to be gone now, and it's north, so I'm not going to worry about it too much. They've got this customer, either the customer that we're working on the house for or the neighbors seem to have some bushes that kind of get up above here. When I have those, I literally just do an obstruction and lift them up like that. Probably be better if you did them as trees if you could manage, but either way, it should have a shading effect or reflect any shading that it might have on the design once we run the radiance profile. This shop's not going to affect anything. They do have a shop out back. Sometimes you can put panels in the shop. This shop's pretty small, and there's all these trees riding against it, so we're just going to pretend like we're not putting solar on it. I also know that you typically have to have a certain amount of panels to fill a circuit. This probably won't fit the amount of panels that we need. I'm going to model in this just in case, but it doesn't look like it's very tall. And then aside from that, I don't see anything massive or major that would cause any shading issues. There is this tree or whatever, probably a palm tree, kind of far away. Same thing though, that's not going to shade on this, especially since it's north. So I just like to be very thorough, but as you can see, we've essentially designed 3 houses. We've got the actual hypothetical customer house. Both their neighbors modeled in for shading and then surrounding trees. So the next thing we're going to do is turn on the irradiance profile. What this is going to do is this is going to show how the sunlight hits the roof, the best areas for panels, and things like that. Now, from what I've found, this feature tends to take a little while. There's a lot of data that it has to aggregate to then display, but here we are, it's displaying it. You can see it for every single house that we've modeled in. We're going to focus on the house that we're designing on. but you can see different levels of radiance. So typically the more yellow or white it is when it's really, really good, like if you do a design in Arizona, the roofs would typically be white. So it goes down from white to yellow to orange to kind of like a red to kind of a purple to then a black. And as you go from white down to black is where the radiance gets worse and worse. As you scan each individual roof face, you will also get some irradiance profile information. So you can kind of determine the higher the number, obviously, the better the solar exposure is. You can also see your solar access percentage and things like that. Typically in solar, at least in the United States, you're going to want to focus on south-facing roof faces. They'll have the best solar access and radiance. This particular customer does not have a lot of south faces that have a lot of exposure, but they do have a nice they do have a nice west face. They do have a nice decently nice east face. They have another nice west face. So they've got some space for panels. We'll get a decent sized system on here. What we're going to shoot for in this particular situation is 100% offsets. We're going to assume that this customer wants to offset the entirety of their utility bill with solar panels if possible. So first thing I'm going to do is try to get panels on these south-facing roof faces. And we're going to roll with 3 80-watt panels. Now, I know typically these bubble obstructions you don't have to worry about too much. You can almost act like the ridge is just going right along here. So I'm going to place this panel here. Then I'm going to place this panel here. And I'm going to say that's the best we can fit on that roof face. We've got 2 panels. We can connect them together. Some companies, some people are going to want to avoid doing as little as 2 panels. Since this is the best exposure roof face and we're saying we're going to place panels in the best places possible or try to shoot for a high offset for this customer, that's where I'm going to stick those first. Next, I'm going to look at the second south-facing roof face, see if I can fit 2 there. Now, that's kind of iffy, but I would say that's good enough. The edge of the panel does not fall into this really low shaded area from this massive chimney. Again, kind of iffy, but LiDAR is pretty dang good. We've got this modeled in fairly large. It's pretty accurate, in my opinion, with shading, or from my experience, I should say, with shading. So we're going to roll with those 2 panels. We've got as many panels as we can on direct south faces. Then we're going to roll to the next best, which is this west face. And we're going to put panels in both orientations to see which orientation we can fit more in. There's 9. There's 9, but I also know we can typically do a little something like this, where we kind of center this array on top of here. It's called top hatting, or at least that's the terminology we typically use. Center this one on here, center this one here, and then center this one on here for a nice little pyramid design. And since we've got 3 arrays set down already, 2 panel arrays and 1 10-panel array, we are going to run our simulation, see what offset we're sitting at, and go from there. I'm not quite sure with this particular customer and the usage that we put in if we're actually going to hit a full offset. I don't think we are, because if I remember correctly, they had about 14,000 kilowatt hours. But you can see right now with 14 panels, 14 380 watt panels, Aurora is projecting that we would have a 53% energy offset, and it spits out the kilowatt hours that the system's going to produce per year. So annually, this system is expected to produce about 7,032 kilowatt hours. So since we haven't quite hit full offset, we're going to continue to place panels. We'll move on to this roof face next, or these 2 roof faces. I'm not sure if we're going to fit a lot here, but we might be able to fit a couple here. We'll see. We might not be able to fit anything, but it's always worth a try. That's super iffy. It's possible we could actually make that work within the fire setbacks. Possible that we might not be able to. In this case, we're going to pretend like we're abiding 100% by these hypothetical fire codes, so we're not going to place any panels in there. We can only fit 1. We need to fit at least 2. There's 8 panels on this roof face. 7 that orientation. Now there's 8 this orientation. Can we flip these and do something like this maybe? And then maybe take this one, center this like I'd shown you guys earlier, put another one up here. Kind of a wonky looking array. I cannot deny this is a wonky looking array, but let's just say hypothetically we're going with that array. That's 9 panels. Let me see if I can fit 9 panels with something a little cleaner, because that's just a little wonky. This is 8. We can definitely fit 9 doing something like that. Maybe we can't. Again, headset died, so it must be about every 15 minutes. So we've got 8 panels like this. This looks really clean. We could fit 9 with a less clean array. Um, So when it comes to things like that, it's going to be up to you or what your company advises or what you want to do if you're running your own business, etc. What I'm going to do in this particular case is I'm going to pretend like this is real California and that that person's not going to want some ugly system on their house. So this is what we're pretty much going to roll with for this customer. Reason being is because we're not going to fit any panels here. This is north facing. It's got a 0 degree azimuth, so it's a direct north facing. I don't know how it works in California, but I would imagine they typically don't place panels in the north there unless it's, unless they're just trying to eke out any little bit that they can. Um, so yeah, and then we couldn't fit any panels here, so that's the best that we can do. We've got an 8.36 kilowatt system with 380 watt panels, 22 of them, 300 watt inverters, which I don't know if you would typically actually pair that with a 380 watt panels, but in this particular software, that's what I've got. So we'll pretend like that's what we're going to use. So I'm going to simulate again, and we're going to see where we go from 53. Cool. So we're up to 78. So as it stands with this particular customer, if they are using about 13,233 kilowatt hours per year, and we're supplying them with 380 watt panels and abiding by 2015 IFCs, the best offset we can get them is 78%. Their system would produce about 10,369 kilowatt hours annually. So I hope that this design video kind of helps some people out. I know it's a little rough, but there are 3 different designs and 3 different types of houses that were designed in this. One Spanish tile house to the north, very quickly, obviously, with a couple different factors, and we did not design these sections in, but I could show you how to do them. Um, we did a mostly flat roof section or a mostly flat roof house with 2 flat roof sections and a pitch section. I did not model in the dormer here, but again, really not going to matter that much. I highly doubt that's going to cast a bunch of shading on the neighbor's house. If you want to be super, super, super thorough, you could always model that in. And then we've got the hypothetical customer's house where we placed 22 panels, an 8.36 kilowatt system with 360 watt panels producing 78%.